me start recording first. Okay. Before I start, need to make sure everyone's here. Okay. Just put an emoji, can, like any emoji. Just put any emoji, and then I know you're here. And then if I see more than 10 emoji, then I think I'll start. Wow, only got 6. Where's the rest? Oh, okay. Wait, y'all know y'all can put it on your screen, right? Not on the chat. Okay, but okay. Can I think can already. Okay, yeah, I hope you are still alive. Okay, yeah, because the next few chapters are the heavy one. Okay. Then let's start. Okay, thermal properties of matter. In this chapter, right, we're gonna learn about quite a few things. Okay, first thing, there's the idea of internal energy. Okay, so actually internal energy, right? What is internal energy? Okay, so later we'll talk about it, and then we're also going to learn about the cooling and heating curve, right? And then we are going to talk about state changes, and then we are going to talk about evaporation and boiling. Okay, so 4 main things to talk about. Quite a big chapter. Okay, so let's just dive into it. Okay, now first one, internal energy, right? So actually, yeah, for my class, I thought you all KE and PE, right? Yeah. So this is happy news. Actually, you don't have to write PE at all, right? Okay. You just use the word internal energy. So what is internal energy? Internal energy is about KE. Okay, so about how fast the particles are moving. You all write PE also can. Actually, you all can just continue writing PE since you all probably used to it already. More used than writing internal energy. Okay, so PE is about how far particles are apart. Right. So if you recall what I taught you all about kinetic model earlier, right? How they are moving is about their motion. How far they are apart is about spacing and arrangement, right? Okay, so that actually sums up the energy system of a particle, right? Inside a solid, liquid, or gas. So we always look at their KE, how fast they are moving, and their PE, how far they are apart, right? Okay, and yeah, so over here we'll start off with the first one, internal energy. So this is the KE plus PE, right? Now, so for KE, so for KE, fast. So to have higher KE, okay, particles need to be moving fast, right? So particles speed increases, and when this happens, higher K, when K goes up, the relationship is that when K goes up, the temperature must go up also, right? Now P, okay, is about how far they are apart. So to have higher PE, the particles, the distance between particles, okay, must increase. Okay, that means this includes expansion and also state changes. Okay, of course, then PE decrease means the distance between particles decrease. That means contraction. Okay, so same thing. This one, if the K goes down, the temperature goes down. Okay, so key things to note: whenever there's a change in KE, triangle refers to change. There must be a change in temperature. Then this one key thing to take note, right? Whenever there's a change in state, there will definitely be a change in PE. In fact, PE is always changing because as long as the distance between particles increase, right, or decrease, right, there will be a change in PE. That means whenever we heat something up or when we cool something down, it will always undergo contraction or expansion, whether or not the object got state change or not. Okay, so I heat up a metal from 30 degree to 40 degree, there'll be expansion already. The metal no need to change state, but it expanded. And because it expanded, the only reasoning why it expanded, right, is because probably the distance between particles has increased. So because it has increased, we say that it has expanded, and therefore the P must have increased. Okay, so now I think some of y'all, right, I think for the H7, H9, I think Madam Ajan didn't really talk about P, which is fine, like really is fine. Okay, but I think she used the word internal energy. Okay, so you can treat P like internal energy like that, right? Because P is part of internal energy. If P increase, obviously internal energy increase lah, right? Okay, so this is the idea of K and P. Yeah. Okay, then we'll go on to the cooling and heating curve, right? So I'll just go through one. Okay. The other one is just the opposite of this. Okay, so I'll already touch on it. Okay, so for cooling and heating curve, you need to take note that okay, something like that. Okay, so if let's say we start off with gas, then this is a cooling curve. So this is a condensation, right? So condensation will be gas plus liquid. Now over here is liquid, pure liquid, right? Then over here will be your freezing, which is a mixture of liquid and solid. Then over here will be solid. Okay, so this is your cooling curve. So very quickly, right, what's happening? Okay, so let's just talk about the liquid first in terms of Ke, right? So obviously the Ke must be decreasing because it's cooling down, so particles move slower now. Because it's a liquid, the motion is slide, so particles slide past each other slower. Now when Ke decreases, okay, so there's always an outcome. So if Ke has decreased, right, okay, then the outcome must be temperature decrease. Okay, if temperature decrease, right, it also means that Ke has decreased. So either or depends what the question asks you So the question offers to you that the Ke of the particles has decreased, right, then your outcome should be temperature decrease. If the question offers you, right, they say the temperature of this liquid has been increasing, then describe the Ke, then you will say that the Ke decrease. Okay. Now over here, during condensation, right? So during condensation, gas becomes liquid. So the spacing, right? What happens to the spacing? The spacing decreases. Furthermore, there's a state change. So this proposes that there must be a potential energy change, right? So potential energy is actually decreasing. Okay. So over here, right? How will you write your answer? Right, so I'll just write a simple one for you. So as the object loses heat to the surrounding, the P of the object decreases. As they become closer. Okay, can? So as object loses heat to the surrounding, the potential energy of the object decreases as they get closer. Otherwise, you can also write as object loses heat to the surrounding, the internal energy of the object decreases as they get closer. Sorry, they as in the particles. Okay, so let me just write it properly so that when you refer, you won't miss out anything. Okay, can? So as object loses heat to the surrounding, the potential energy of the object decreases as the particles get closer. Okay, so that's the idea of condensation. Okay, so state change, no Ke change, right? So you can also continue since no change in Ke. So no change in Ke, so a lot of students love writing this, okay? They move slower, okay? So no change in Ke means you cannot write. Okay, so move slower. Phrases like that, you must avoid writing. Okay, because move slower suggests that there's a change in speed. When there's a change in speed, it means that there's a change in Ke. So since no change in Ke, therefore no change in temperature as well. Okay, so this is the full explanation. Okay, so part 1 and part 2 as to what's happening during condensation. So during condensation, object loses heat, particle potential energy of the object decreases, particles get closer together, and then since there's no change in Ke, there's also no change in temperature. Okay, because it's losing energy in the form of potential energy, right? That means they end up getting closer together. Okay, this cooling curve explanation, any issue? Okay, if not, I'll move on. So we finished cooling curve, state change. The last one is evaporation, boiling. Okay, so for evaporation, now evaporation versus boiling. Now, boiling is a process at a fixed point, whereas evaporation is not, right? So a liquid can undergo evaporation at any temperature, right? Obviously, once the liquid freezes, right, it's no longer a liquid, so it won't evaporate. Okay, you don't see solid evaporating away. If solid evaporates, right, that means everything you possess right now will suddenly disappear one day because evaporate away. Okay, so solid don't evaporate, only liquid. Okay, and liquid evaporates at all temperature, right? Okay, so evaporation versus boiling. Now the idea of evaporation, right, is as such. Okay, I have a
teacher, I want to ask something.
yes.
When you talk about like, for example, boiling, then when you talk about boiling, you have to talk about temperature is constant because the energy is being used to overcome the forces of attraction.
Yeah, yeah.
Right.
Temperature is constant because there's no change in Ke. Number one. Okay.
Then what do you talk about potential energy?
So energy is gain, right?
Hmm.
Energy is gained as potential energy as the particles move further and further away from each other. Yeah.
Okay.
Can?
Okay. Yeah. Okay.
So you need me to write, or you write down on your own. Okay. So what happens at evaporation, right, is that I have particles with higher energy at the top layer, right? So these are particles of high energy. We call them high Ke lah. Specifically, we are looking at Ke this time. Okay. Now, the average temperature of the water, right, is at a certain value, right? But because it's an average temperature, that means there will be portions where the water is actually warmer, slightly warmer than the rest. Okay, and that slightly warmer part, right, is the part where the particles have actually high Ke, right? Okay, so what happens is that the particles with high Ke escapes the surface, right? So when they escape the surface, okay, so this actually lowers. Sorry, I think someone needs to be muted. Ryan, I'll mute you, okay? Okay, so of course you got a question, you can unmute yourself. Okay, so anyway, this lowers the average Ke. Okay, so it doesn't lower just the Ke because not every particle share the same Ke, but it lowers the average Ke, okay, of the liquid. Okay, by the way, take note, the context is about liquid, right? Liquid, don't suddenly change to water. Liquid doesn't mean water, okay? Water is a liquid, but not all liquids are water. Yeah, so this lowers the average Ke of the liquid, which creates a cooling effect, causes liquid to cool down. Okay, because when the Ke decrease, so same thing, always relate it back to temperature, right? So whenever we talk about Ke, try to always relate to temperature. Okay, so that's the idea of evaporation. So obviously, if your surface area is larger, that means more particles can escape at one time. Okay, then obviously your rate of evaporation will increase. Okay, yeah. So that's about it for thermal property. Okay, then
Does temperature affect?
temperature effect, yes, because if temperature is higher, then average Ke should be higher also.
Okay.
Then average Ke higher means there will be more, by statistics, there will be more particles with higher Ke. Right?
Then technically doesn't boiling evaporation happen at the same time?
Yes, it can happen at the same time.
Okay.
Thanks, Yang. Yeah. Okay, so evaporation is an event that keeps occurring. Okay. Okay, then if everyone's okay, then we'll move on to the last 4 chapters of what we have today. I think the 4th one is the easiest. Okay, so we have wave, light, and sound. Okay, so let's go to waves now. Okay, yeah. Sorry, give me a minute.
没有跟你买画纸。
Okay, yeah. So now we'll go to waves, right? So I think the very first 2 things that you learn in waves are transverse and longitudinal. They both have similar phrasing, so the particles in the wave move in a direction, so either perpendicular or parallel to the wave travel. Okay, that means one is when my particles move from left to right. When my wave moves from left to right, right? So this is the wave travel, right? My particles actually go up and down, and this creates a wave that looks like that, right? The other one is when my wave moves from left to right, my particles also move left to right, so it actually creates a wave that's like that. Okay, so the particles will move left and right now. Okay, whereas the particles here, they go up and down. Okay, then go up and down, then you bring them left to right, they'll be like that. This one move left and right, then you bring them left and right, then you go like that. Okay, so I think this one you all should know the answer lah, right? So I won't go through.
Wait. So longitudinal is the second graph.
Yeah, of course.
Okay.
Can? Okay, so okay, so this is the idea of waves, and I think the period, frequency, all this I won't go through lah. Should I go through? You all know, right? So period is the time taken for one complete wave. Okay, I better write now. Then frequency is the number of waves in 1 second. Okay, now combining these two, right, there's a formula that relates both of them, and that's t equals to 1 over f, or f equals to 1 over t, whichever you want to memorize. Okay, no need memorize both. It's just a manipulation of one another, right? Okay, so that's the idea of period and frequency. Okay, then we'll move on to the 2 main graphs that we learned in this chapter, which is your displacement time, right? So really, displacement time looks like that, but it doesn't mean that the particle is moving up and down. Okay, it can be moving left and right also. Displacement is just positive and negative. It looks like it's moving up and down, yes, but this upper part just means positive displacement, and positive displacement can be moving to the right, and if that's the case, right, then negative displacement will mean moving to the left. Okay, but anyway, the characteristic is as such. This is the amplitude, and one complete wave gives us the big T, which is your period. Okay, the amplitude is how much they move away from equilibrium. Okay, so equilibrium will mean their original position, right? And the second graph we have here is our displacement time. Displacement distance, sorry. The graph looks similar, but it tells of a different quantity. Now over here, this is your lambda, which is your wavelength. Okay, so wavelength is the distance traveled from one point to another, either 360 degree, or one crest to another, or one throw to another, right? So this is your crest, this is your throw. Okay, so That's the definition of wavelength, right? It's just a distance, but it's from one point to one point. Okay, this is another C, this is another T. Okay, my graph not long enough, but if you continue, it will look something like that. Yeah. Okay, so yeah. Okay, if we combine these two graphs, right, we actually can get a formula, right? So big T from the period, we can actually find frequency. Okay, so we call that F equals to 1 over T. So we combine these two, right, we can actually get this formula V equals to F lambda. That means from this graph, from these two graphs, we can actually deduce this. We can actually obtain and apply this formula, right? Of course, this formula is really just from speed equals distance over time. So a quick derivation for you, right? So speed equals to distance over time. So we can use this formula only when there's constant speed. Now, thankfully for your waves, so the assumption is that there's constant speed. Thankfully for your waves, the speed is always constant unless the medium suddenly change. Okay, so if I talk, right, the speed of sound in air is about 330, and it will continue remaining 330 until there's a change in medium. Yeah, maybe it touches a liquid or touches a solid. Otherwise, the speed is quite constant, right? So the assumption is constant speed, and for waves, we can do this because the speed is constant. Okay, your kinematics cannot, because most of the time the object is accelerating. Unless the speed is constant, then you can use this. So anyway, speed equals distance over time, and the amount of distance you move, okay, we can call it lambda. And to move lambda, right, I actually need one period. Okay, so it becomes lambda times 1 over T, which is basically our F lambda, right? Because this part here is F. Yeah. So then we have V equals to F lambda, which is the formula, the main formula for this chapter. Okay. Yeah. Then, if not, I think I'm just left with one last part for this chapter, which is the wavefront part. Okay, so wavefronts, they are imaginary lines joining together the crest of the wave. So it's just an imaginary line that actually doesn't exist. In phase, right, means they are moving at the same angle. That means at the same point. Okay, that joins the crest, they are in phase together. Okay, yeah, while it looks very complicated, really, right, if we have a rectangular bar hitting against a water, okay, so we take a rectangular bar and then we let it hit, vibrate up and down, okay, and on a pool of water, right, it will start to produce wavefronts that look like this. Okay, so these are actually your wavefronts, right? And the distance between each wavefront is lambda. So remember to include your scale whenever you draw wavefront.
Sure, if it's 5 wavefronts, then is it the gap or is it the line?
5 wavefront means 5 lines.
5 lines.
But 5 wavefront got 4 lambda. Right. Correct. So I just drew 5 wavefront. How many lambda are there? 4, right?
Yeah.
Okay, can. Of course, please use a ruler. I never use a ruler, okay? So the spacing looks a bit off. And my line is not straight, okay? So,
Mr. Ko,
yeah.
wavefront, I thought it's like the imaginary line joining the crest and the throw. Or is it just only crest?
Crest, because the throw usually cannot see on water.
Oh, so it's only crest.
Yeah.
Okay.
Yeah, because the throw is below the equilibrium. Equilibrium is where the water was previously, which is the flat surface, right? So the throw is below the flat surface. You cannot see below the flat surface. Yeah. Okay, can. Yeah. If not, then I think that's it, right, for this chapter on waves. Yeah. Anyone don't understand wavefront? I can show you an animation. Y'all need that? Anyone need? No, if not, yeah, so same thing. I'll put an animation link here. Yeah, please go and try out the animation for wavefront if you don't understand wavefront. Okay. Then if not, we'll move on to the a very big chapter known as light. Okay, so light got reflection, refraction, and lenses. Okay, so 3 parts. So you go through reflection first. Okay, things that yeah, I'll focus mainly on the diagrams and the conditions, okay, and some statements, okay. But things like characteristic, I want like characteristic of a image for my plane mirror. That's on your notes, okay. So I leave it to you to actually go and figure out what's the characteristic. Yeah. Okay, so for mirrors, the reflection is quite straightforward. Okay, so if the object is here, first thing first, the object and the image must be the same distance away from the mirror. And because it's a virtual image, how you know it's a virtual image? Because it cannot be formed on the screen. Now, all of y'all have done same practicals throughout the year. Okay, one of your practical involves light. In fact, two of your practical involves light. Okay, so you shine a torchlight through the very flimsy paper with a triangular hole in between, right? Yeah, and then you try to form that image onto a screen. That one is real, okay, because the image can appear on a screen. Now, virtual means the image actually appears on the mirror or on the lens itself. For example, magnifying glass, the image is on the lens itself. Okay, for example, your mirror, the image is on the mirror itself. Okay, you are 2 meters away from the mirror, right? Okay, on the mirror it looks like you are 2 meters away, but the image is actually on the mirror. It's not like 2 meters deeper than the mirror. Okay, when you go behind the mirror, right, like 2 meters behind the mirror, you actually don't find the image there. Yeah, that means it's a virtual image. Okay, so this is a virtual image. Virtual image are denoted by dotted lines. Okay, then your eye is here. Okay, so all you need to do, right, the first step is to draw the image. Okay, draw virtual image. Okay, the second step is to draw the lines, okay, from the image to the eye. Okay, but I can't do it very well here because it needs to be dotted. So I'll try my best. Okay, ayo. See, there's refraction already, and that's not supposed to be. Okay, so this is the second. So draw ray from object to eye. Okay, can? Then after that, the third one is to draw rays from this one not object, sorry. This one is image. Then this one is object. Okay, so the third step, right, is to draw ray from object to mirror. Okay, so these two main points, right? Okay, so please draw your rays from object to the mirror at that point. Okay, and then lastly, right, okay, please don't lose mark because of this. Draw arrows, right? So what color have we used? Yellow. Okay, step number 4, arrows. Okay, now if let's say they change the orientation of the mirror, right, and you don't know how to do, right, then just tilt the paper lah. So you tilt the paper until the mirror looks like that. Okay, then I think you should be able to draw again. Can? So just tilt the mirror a bit. Okay, so that's it for reflection. Okay, there are 5 characteristics: same distance, laterally inverted, yeah, same size, virtual, and can't remember the last one. Okay, but there are 5 lah. Okay. Okay. If not, then we'll move to refraction. Okay. By the way, the law of refraction, I think you all should know already, so I'm not going to go through. Anyway, later at critical angle we will revisit that. Okay, so for refraction, so there are a few formulas. So n equals to sine I over sine r, which is equals to also sine r over sine I, depending on the situation. So I'll write the condition below, which is equals to c over v, so the speed ratio. Okay, so remember, c is the faster speed, or rather the speed in the less dense medium, and this is the slower speed, which is the speed in the more dense medium. Okay, for those who are not with me before, I'll use this term whenever I visit this chapter, which means OLD means optically less dense, and then obviously OND means optically more denser. Okay, so this is the slower speed is actually the speed in the OMD medium, and then this is the speed in the OLD medium. Okay, now then there's conditions. Okay, so the sine I over sine R cannot be sine R over sine I unless there's some condition. So the condition for sine I over sine R is that light is traveling from OLD to OMD. By the way, if that happens, this is bent towards normal. Okay, whereas this one is for OMD to OLD. That means maybe glass to air. Then this is bent away. Okay, and N, right, is known as my refractive index. This value tells me how much light will bend. The higher it is, then the more light will bend. Yeah. By the way, it's a trick question. Okay, it seems like whenever light bends, your angle of refraction wants to increase, but actually it's not right? So if this is air and then this is glass, right? So if my refractive index is higher, I bend more, right? Okay, so maybe at first I bend like that, right? So that's bending already. Then I tell you I increase the, so where's my angle of refraction? My angle of refraction here, right? Then they say I increase the refractive index of glass, right? So now I bend even more, right? So I bend here. So what's my new angle of refraction? It's actually smaller. Okay, so the more you bend, okay, the smaller your angle of refraction. Okay.
Joe, what's the definition for for N?
It's a ratio. It's a ratio of the fast. That's is the ratio of the speed of light when it goes from a less dense medium to a more dense medium. Basically, this is the definition using the formula C over V. You need me to write down?
No.
But I think maybe the rest need. Okay, can. So ratio of speed of light as it passes from OLD medium to OMD medium. Okay. Yep. Okay, so let's try out some scenarios. Okay, so there are a few scenarios to try out. In fact, there's I think the very basic one. We try the very basic one first. Okay. So if I have a light coming in here, okay. So first, please draw the normal. Right, the normal is the line perpendicular to the surface, okay, or perpendicular to the tangent if it's a curved surface. Right, so this is your incident ray, this is your angle of incidence. Now if this is air, then this is glass, then it's quite simple, right? The light will just bend towards the normal. Okay, so complicated stuff coming is when glass goes to air, right? So this one we just use n equals to sine I over sine R. Okay, but then there are 4 different cases if you are talking about glass to air. Okay, and these are the 4 cases. Okay, so I'm going to create a box, and then we are actually label it with 4 cases. So 1, okay. So first case, very simple, right? I have a surface. Light enters perpendicular to the surface, no refraction. Okay, so quite straightforward. So this is air, this is glass. Sorry, I should use a different ink. Yeah, let me use this. Okay, this is glass, and then this is air, right? So no goes through straight. Okay, when this is when I equals to 0, right? There's no angle of incidence here. Okay, now for the next 3, okay, maybe you can just draw the boundary first. Okay, and then yeah, different angle of incidence. So remember, this is glass to air. Yeah. Okay, so this is the case when I is lesser than C. Now C is a special angle, it's known as a critical angle. Okay, critical angle is really just a value. Okay, it's something like I tell you your critical weight value. So maybe last time when I was younger, my critical weight value was 75 kg. If once I hit 75, that means I overweight already. Yeah, So that's my critical weight value. Yeah, critical angle works something like that. It's a critical angle, which is really just a critical value. So something special will happen once you hit that value, and once you hit more than that value. For example, like myself, right, when I was younger, right, 75 kg. What happens when I hit that value? Then that means I really need to watch out my weight. You know what happens when I exceed the value? Oh, means I overweight really. Yeah, so same thing for this. The critical angle, right? If I'm below critical angle, okay, things are quite normal, you know. But once I hit the critical value, maybe my blood pressure, like something will happen to my blood pressure. So over here, something will happen to light. Now once I'm more than my critical angle, right, my blood pressure definitely quite high already. So something else will happen to light also. So there's three conditions here: I less than C, I equals to C, I is more than C. Okay, so my critical value is really just my critical angle is really just a critical value, and every medium, right, has a different critical angle. Okay, yes, Zheng Yang.
Is there like a definition for like the critical angle? Because like they also define before, right?
Have.
A lot of the testing.
Yeah, over here lah. So I'll define the third box.
Okay.
When I is equals to C, then easier for me to talk about. Okay. So you can label it like that first, right? So when I is lesser than C, all the light does, right, is that it bends away. Okay. So take note, I only talk about C when light travels from optically more dense medium to optically less dense medium. So maybe this is glass, and then this is air. Okay, so this one is just bends away from normal. This one quite straightforward, right? And this one we can actually use the formula n equals to sine r over sine I, because in this case, okay, just take note that the larger angle must always be on top. Okay, so if you mix out the formula, it's okay. Just make sure your larger angle is on top. Whenever you do this formula, I want you to do a check. Ask yourself, is my numerator angle greater than my denominator angle? Because n must always be more than 1. Therefore, the numerator must always be bigger than the denominator. Okay? Okay, so next one is when I equals to C. So when I equals to C, we also have another formula. We have n equals to 1 over sine C. And what happens is that the light ray, right, will actually travel along the surface. Okay, so it travels along the surface. I'll use red, more obvious. So same thing, this is my glass, and this is air. So when I equals to C, light travels along surface. Okay, so what is C? C is the critical angle. So what is the critical angle, right? So give me a minute. Let me just draw up the definition. Okay, sorry, maybe I type out a bit long. Wait. Okay, can. So basically your angle of refraction is 90 when your I is equals to C. Let me just readjust everything. So when your I is equals to C, your angle of refraction is actually 90 degree. Okay, so then we use that to actually define critical angle. So critical angle is an angle of incidence, but it is an angle of incidence when light travels from this to this, which causes the angle of refraction to be 90. Okay, Now finally, right, we have our last one, which is really, right, when I is more than C. So it's kind of like overweight, right? Like if we use the analogy from earlier. So what happens? So over here, TIR will occur, right? Okay, so TIR occurs. So this is from glass to air, and TIR occurs. Okay, so this is my angle of reflection. So TIR occurs. Okay, so remember law of reflection. Okay, that means the angle of incidence is equal to the angle of refraction. Okay, and these are your 4 diagrams when it comes to OMD to OLD. Okay, so
F or I.
sorry,
The one next to it.
the one next to reflection.
Wait, no, the one, the green one I.
Yeah, okay, can. Now there are 2 conditions for TIR to take place. Firstly, light must go from OMD to OLD. The second will be I must be more than C. Now today's technology, one of the most obvious technology that is using TIR today is the reason why we can have zoom also is our optic fiber. So our optic fiber inside got a lot of glass. Then in the glass, TIR actually occurs, right? Okay, so when TIR occurs, it actually allows internet data to be transmitted near the speed of light. Yeah, that's what we want. Okay. Last time it used to travel through LAN cables, which is much slower. So optic fiber, 2 reasons why it's good. Okay, number one, it's actually cheaper. Okay, compared to you building landlines underground, right? Optic fiber is much cheaper. It's lighter also. Okay, so it's lighter, it's cheaper, and it's faster. It's definitely much faster. Okay, okay. Otherwise, really, we wouldn't be able to do this at all if not for optic fiber. Okay. Okay, so last part of light, so this is the refraction part. So last part is lenses. Okay, so lenses, I will go through 2 main images. Okay, so I'll draw 2 ray diagram for you. Okay, there are 6 in total. Okay, but I think you can actually do it on your own. Okay, then yeah, let me just start. So if I F here, F will also be here. Then this is 2F. Then this is also 2F. Now I'll put an animation here. I want you to try out the animation on your own, and then you'll actually be able to see, right, what happens to the object as it moves from infinity to before F. Okay. By the way, also if I have an object here, that means my object is between 2F and infinity. Now to draw the ray, I just need to do this, right? And then I have my next line, which is go straight, and then I cut F. Then the intersection will be where my image is. So this is my image. Okay, I can draw it in solid line because this is a real image, right? And the characteristic here is inverted, real. By the way, these two always go together. Whenever it's real, it will be inverted, and then this is diminished. Okay, because the size is smaller. Okay. Now, whenever it's real, it's inverted. So please take note how you draw the arrow also. Okay. Okay, the next one I want to do, right, is a virtual image. So if my object is here, you'll realize that when I draw my first ray, which is the one that cuts the middle, then I draw my second ray, I actually don't get any intersection. They are widening, right? Okay, so then where's my object? So now this is a virtual image. So for virtual, we'll label it with dotted line. So I need to just extend indefinitely these 2 lines to the point where they intersect. So if this is the point they intersect, then this is where the image is. Now we dotted it because once again it's virtual. So in this case it's virtual and upright. Okay, by the way, these 2 always goes together also. So whenever it's virtual, it will be upright, and in this case it's magnified. Okay, of course all these diagram will minus 1 mark because I never include arrow. So please include your arrow. Okay, and then that's about it. Okay, of course then there's the idea of magnification factor, right? Okay, so yeah, it's just the image over object. Okay,
So it's diminished when it's
smaller.
image is smaller.
Yeah. Okay, so same thing, I'll put a QR code later over here when I send you all the notes, and then over here I want you to go and try out. Okay, so I'll write here lah. Okay. Okay, so try and see how the how image changes as object goes from infinity to before f. Okay, so later on in the simulation you'll be able to shift the object from here, this position, all the way to before here. In fact, you can shift it even to f lah. It's okay. Yeah, then you can shift it to beyond f. Okay, then you'll be able to see. Okay, okay, so so lenses. Okay, now someone asked, so what does it mean for refractive index to be high or low? So high refractive index means my light can bend more. Low refractive index means my light will bend less. Okay, so n is just telling you how much light will bend. The higher it bends, then the higher the n. Yeah, that's about it. Okay, yeah, if not, then that's it for light. Okay, so please try your light TYS. I think the questions there are quite good, and it actually allows you to practice drawing. I think that's one of the main thing that students are stuck with. Okay, so we are done with almost everything. Now we're left with sound and EM wave. We are on track, we are on time. Good. Okay, so I'll go through the smaller chapter first, which is EM wave. Okay, so EM wave, right? Really, right? You just need to know a few things. So first thing, you need to know the order, right? So the order will be gamma ray, X-ray, UV ray, visible light, infrared, microwave, and radio wave. Okay, then I need you to take note. Now for all your phone communication, right? Okay, we actually use radio wave today. Okay, yeah, it's a bit blurred lah today, really, because when people use phone now they got 5G and then 5G is in between here. So I think they will stop asking phone questions very soon, or they'll make it more specific. Yeah. Okay, but because phone region is here, last time, right, it used to be here, so that one quite obvious. Yeah, but as more and more network comes out, so many this was 1G lah, then 2G, 3G, 4G, 5G. Yeah, and then it's steering towards radio wave. Now the reason why radio wave is good, right, is that this is the longest wavelength. So with the same amount of energy, you produce the same number of then this is the shortest wavelength. Okay, so in terms of energy transmission, right, the longest wavelength is good because it can travel further away, and that's what you want your phone to do. It doesn't need to be like super high energy, right? You don't need to hear everyone at maximum volume all the time, right? Yeah. I thought like that you also can listen, so I think it's good, right? But of course, it must be of a certain energy lah, right? Okay, and they are just transmitting data, so the energy actually comes from a loudspeaker, right? Okay, so radio wave has longest wavelength, that's why it's good for communication. Now gamma ray has shortest wavelength, and these two, they ionizes. That means they actually refer back to your chemistry, right? Ion means that it creates, not creates, it allows the electron to go out of the atom, or allows electron to come into the atom, right, creating an ion. So ionizers means they actually change the atomic structure, and therefore they are harmful, right? So I know a lot of us, some of our parents may suggest that microwave is harmful. Microwave is super far away from gamma and X-ray. If microwave is harmful, right, the first thing that's harmful, right, will be your visible light. Okay, that means you all should be live in darkness, okay, because it's harmful. Okay, so but no lah, okay, visible light is not harmful. Okay, so microwave is also not harmful, right? Okay, it's more like microwave can cause things to explode. Then that's the harmful part, if anything. Yeah, okay. So if you put an egg in the microwave, it should explode, I think. Yeah, because of the air inside the eggshell. Okay. Now UV ray long exposure causes skin cancer. I think what you all need to memorize here is the application. Okay, and take note that the properties of it. Right. So properties. Let me run through some properties.
Wait,
Okay.
Mr. Go, I thought you said that time internet is microwave.
Huh?
Wait, I thought internet is microwave.
But Wi-Fi is radio wave leh.
Oh, okay, then never mind.
So yeah, I mean it's a mix I think I put here lah. Better. Can?
Yeah.
It's really a mix.
But do we have to know like actual length of the radio wave all this?
Sorry? The wavelength?
Yeah, do you have to know the
No need.
Mm.
Yeah. Then travel at 3 times 10 to the power 8 meter per second. Only in vacuum. So in other medium, it's not really. In other medium, it behaves like light. So remember previous chapter we talked about light, and then it seems like light speed will change when it undergoes refraction. So same thing. Okay, light speed will change when it undergoes refraction. Okay, so they transverse wave travel at 3 times 10 to the power 8 meter per second in vacuum, and then they transfer energy. Okay, so I think 3 things to remember. Okay, now another last thing to remember in this chapter, right, is that for visible light, red is here and blue is here. Okay, I need you to memorize the wavelength. So this is 700 nanometer, which is 7 times 10 to the power minus 7 meters. And then this is 400 nanometer, which is 4 times 10 to the power minus 7 meters. By the way, shortest wavelength also means highest frequency. And then longest wavelength also means the lowest frequency. Okay, can? So that's it for EM wave, and then we can go to sound already. Okay. Any issue with EM wave? Okay, so these two must remember. This one important.
Why shiny got blue and red one?
Visible light got 7 colors, right? 7 spectrum of color, right?
Oh, okay.
Yeah. So we have the blue light and the red light, and the blue light has a wavelength of 400 nanometer, while red light has a wavelength of 700 nanometer. This one good to know. Good to know. I don't think they'll test extensively, like state the wavelength of blue light, but it's more like they will tell you, I have red light and I have blue light. Which one has higher wavelength? So it's good to know. Okay. Then we move on to sound. So far, everyone alive, Okay, last chapter, guys. Yeah, if you're not alive, we will slap ourselves awake. Okay. Yeah, I know how tough it can be for revision class to be like that, but no choice. It's like a crash course. Okay, so sound. First thing first, sound is a longitudinal wave, and it transfers energy through pressure, not vibration. Okay, the vibration creates a pressure difference for the energy to be transmitted that way. Okay, so we actually need to learn how to describe how is a sound wave produced. Okay, which is I think most commonly one of the things that students cannot remember how to write. Okay, so because of that, I'm going to type out for you all. Right, so when a disturbance occurs, it causes particles in the medium. Okay, so the second line is quite important. So this pushes together and pulls away the particles continuously, creating a series of compression and refraction.